So chapter 13, 12, chapter 12. Systems of linear equations, inequalities in three variables. So this is very, very similar to what we did for systems of equations in two variables. So section 12.1, systems of linear equations in three variables. So let's recall. Um, so a system of equations, well, let's say ax plus, well, let's not call it, yeah, okay, let's do it. Ax plus by plus, well, rather than having two variables, I have three variables. Cz equals d, ex plus fy plus gz equals hi x plus j y plus kz equals l. So this is a system of, so this is a system of simultaneous linear equations. In this case, this will be in three variables, at least what I've written. So recall that I gave you several techniques. One was the graphing method. In more than two variables, it's not really very practical to draw to try to draw these. So we won't actually be using that technique of graphing, but at least I will, at least for three variables, show you what it means, and then that's all I'll do. So I'll just sort of say, well, this is what it means to what a solution means, but it won't really be a practical technique to actually solve systems. Next, substitution. We will be doing substitution, but usually not for systems of equations, but of linear equations. But we might be doing it for systems of nonlinear equations. But in general, we usually don't use substitution. Next, elimination. We'll mostly be using elimination, but the elimination is a little complicated. So we'll actually give you some hard rules to say, well, this is actually how you should be solving the system so that you don't get lost in sort of all the options available to you. So we'll say, well, you do it this way, and if you only do it this way, then you won't get confused, and that's how we'll say that you'll solve these systems. For the matrix methods, And then the last one is determinants. I'll sort of give you a hint at the matrix methods, but we really won't do it. And I will show you how to use determinants to solve systems. Okay, so first off, I guess, let me classify solutions. Okay, so suppose we have, in this case, a say equation of the form ax plus by plus cz equaling d. Well, in general, that will look like some plane in space that goes on forever. So it's some sort of plane in space. You can think of it as, I don't know, if you look at the top of a desk, it's just the top of a desk. It keeps going on forever. Or maybe if you look at your wall, and it's your wall of your classroom or whatever, or the roof, the ceiling of the classroom. That's a solution. And so, suppose I have another equation. Well, it's another plane. And then lastly, let's pick another plane. And so these will all intersect at one point. And so these could, if they're all going at like different angles and etc., they could all intersect at one point. So let's say if you looked at, I don't know, your ceiling and two walls, notice that there's a corner where all three of those intersect. So that would be a solution of your system of equations. And so this has one solution to this system of three simultaneous linear equations. And so this is called a consistent system. Again, it's also independent. But usually I don't say that. I just say that that this is the case of a consistent system. Okay, let's look at the case of, well, suppose I have, well, a plane. So these are, well, I guess I should have called that something. These are intersecting planes. So this is the case of intersecting planes. Now let's look at the case where I have, let's say, this plane, this plane, and this plane. So in this case, we have three parallel planes. And so in that case, there's no solution. So the number of solutions is 0. Okay. So this is called an inconsistent system. Again, well, it's independent. We could also have the case where you have, well, say, so we have two parallel planes. And so in that case, we'll actually have that two of the planes will intersect, yeah, and you'll have these two pairs of intersecting planes, but the lines that they intersect upon will actually be parallel lines. So we have two parallel planes. So that's again another case of having no solution. And so this is an inconsistent system. Next, suppose we have one plane, two planes, that are the same, and let's have three planes that are the same. So there are three coincident planes. In which case, we have an infinite number of solutions. In fact, every point on the plane will be a solution. And so the solution is every point on that plane. Well, I'll say that this is the case of a dependent system. And, well, these, of course, are also coincident. Consistent. So it's a dependent system that's also, of course, consistent. Um, since every point on the plane is a solution, then we have what's called a two-parameter family of solutions. And so we will be able to describe the solution by having two different variables. So when I actually describe the solution, I'll have to write it with two different variables. So next, we could also have the case where we have one plane and another plane intersecting along, let's say, some line, and then we have another plane also intersecting along that line. And so the intersection will be, in this case, instead of every, actually I should probably fill this in saying that every point on the plane is a solution. Here, every point on the line is a solution. And so this is the case where they have one line that is the same. And so this will give you a one parameter family of solutions. So the actual solution will just be a line as compared to a plane. Okay, so let me give you some notation, and let me actually do this. So let me do some examples here. Let's say on page 512, let's do problem number 2. So first equation, I'll call it R1. 5x plus y minus 2z equals 2. Second equation, x plus 7y plus 3z equals negative 3. Third equation, negative 2x minus y plus z equals 0. Okay, so the first thing you have to determine is what variable you want to keep and which ones you want to eliminate. So I should see what variables have 1s in front of them. I want to keep those. Well, actually, this has got a 1, that has a 1, and this has a 1. So it doesn't matter. I could either keep x, y, or z because they all have 1s in front of them. So now the default is to look at, well, which ones are easier to eliminate. And so in this case, I have a 5 and a 2, not as easy. A 1 and a 7, well, I can eliminate the 1 easy. Unfortunately, 7 is kind of a big number. A 2 and a 3, again, so either keep the eliminate the y or eliminate the z. Okay, and so in this case, it'll probably be slightly easier if you eliminate z. So let me take. So I'll eliminate z. So once you start to eliminate z, you must use all equations to eliminate z. And so your rule of thumb is I have 3 equations. I must use all 3 equations to eliminate z. If I don't do that, then I will go around in circles and I will not get to my answer either quickly or I may never even get to my answer. So you must always, if you start to eliminate one of the variables, you must keep eliminating that until you've used all of the equations and that variable has been eliminated. And so notice that I have a 1 in front of this z and a 2 in front of this, a negative 2 in front of this z. So let's keep the first equation, 5x plus y minus 2z equals 2. And let's multiply the third equation by 2. Negative 4x minus 2y plus 2z equals 0. And add. If I do that, actually let me move this over slightly so I can show you my plus sign. And so let's add. If I do that, I get, well, 5x minus 4x is x. Y minus 2y is minus y. The two z's cancel, equals 2. Let me call that a new equation, S1. So I have eliminated z using the first and third equation. I never used the second equation. So I must keep going on to eliminate z using the second equation. So let's write the second equation, R2, x plus 7y plus 3z equals negative 3. Multiply the third equation by negative 3, 6x plus 3y minus 3z equals 0. Add the second equation minus 3 times the third equation. And so if I add these, well, the x plus 6x is 7x. The 7y plus 3y is 10y. The 3z's cancel, equals negative 3. So I get this a second equation. So now I have two equations, two unknowns, which is identical to what we've solved before. So now we do the same sort of thing. Maybe in this case, since it's easier to do this, I'll multiply the first equation by 10 and add. And so I get 17x, 10y's cancel, equals 17. Divide both sides of my equation by 17. And so x is equal to 1. So now I can figure out what y and z are. I can plug into any equation so that so long as the equation involves my one unknown. So I know my x, I can figure out my y. Maybe I'll use S1. And so x minus y equals 2. Subtract 1 from both sides. And so I get negative y equals 1. Divide by negative 1. So I get y is equal to negative 1. So I know x, I know y. I want to figure out z. I can probably use third equation. So let's use R3. And so R3 says negative 2x minus y. So negative 2x minus y plus z equals 0. And so negative 2 plus 1 plus z is 0. Negative 2 plus 1 is a negative 1 plus z is 0. Add 1 to both sides of your equation. And so I have that z is equal to 1. Therefore, my solution is the ordered pair x is 1, y is negative 1, z is 1. In general, I'm lazy and I actually don't write the ordered pair. I usually just say, well, x is 1, y is negative 1, z is 1, and just assume that you can write it as an ordered pair. Let me do problem number 6. So the first equation, and it is a very good practice to actually label each of these equations, because if you don't, it is very possible that you will get lost and you will not remember which equations you have used, which equations you haven't, and then you'll go around in circles and get lost in the desert. And so 2x plus y minus 3z is equal to negative 1. Second equation, 4x minus 2y minus 3z equals 3. Third equation, 2x minus y plus 3z equals 3. So actually it looks like z is actually easiest to eliminate, because if you add R1 to R3 and R2 to R3, you eliminate z. And so that actually looks pretty easy. So why don't I do R1? So I will eliminate z. So let's do R1. Two x plus y minus 3z is negative 1 plus R3, 2x minus y plus 3z equals 3. Let's add these. So I get 2x plus 2x is 4x. The y's cancel, the z's cancel, equals 2. And so divide by 4, x equals 1/2. So I've actually already solved for one of the variables. X is 1/2. Let me do R2 4x minus 2y minus 3z equals 3. R3, 2x minus y plus 3z equals 3. Let's add these. So I get 4x plus 2x is 6x, minus 2y minus y is minus 3y. The 3z's cancel, equals 6. Notice that x is 1/2, so let's replace x by 1/2. And so I get 3 minus 3y is 6. Subtract 3 from both sides of my equation. So I get negative 3y equals 3. Divide both sides of my equation by negative 3. And so I get y is negative 1. And so I can use any one of these equations to figure out z. And I guess it really doesn't matter. They're all about the same. So the only one that has a plus sign is R3. So why don't I use R3, I guess. And so 2x minus y plus 3z equals 3. And so 2's cancel, so you get 1 plus 1 plus 3z equals 3. So 2 plus 3z equals 3. Subtract 2 from both sides of your equation. And so I get 3z equals 1. Divide both sides of my equation by 3. And so z is equal to 1/3. So x equals 1/2, y equals negative 1, z equals 1/3. Okay. let me do problem number, let's say 24. Three x minus 5z plus 1 equals 0. 2x plus 7y minus 6 equals 0. X plus y plus z minus 5 equals 0. Okay, so first thing to do is for the first one, well, let me subtract 1 from both sides of my equation. And so I'll get R1 will be 3x minus 5z is negative 1. Let me add 6 to both sides of my equation. 2x plus 7y equals 6. So again, now the only x, y's, and z's are on the left-hand side, so I'll call this R2. And lastly, let's take my last equation and let me add 5 to both sides of my equation. And so x plus y plus z equals 5. So that's R3. So let me list these down. R1, 3x minus 5z equals negative 1. R2, 2x plus 7y equals 6. R3, x plus y plus z equals 5. Okay, so if I look at this, well, notice that for this first equation, y's been eliminated. For the second equation, z's been eliminated. So it'll be easier if I eliminate either y or z. Z seems to be easiest to eliminate. So let's eliminate z. So eliminate z, I only have to use R1, 3x minus 5z equals negative 1, and 5R3, 5x plus 5y plus 5z equals 25. If I add, then I get 8x plus 5y, z's cancel, equals 24. So let's call that S1. And R2, I'll call that S2. 2x plus 7y equals 6. So now I have two equations, two unknowns. So let's multiply the second equation by negative 4 and in order to eliminate x. So let's eliminate x. So I have S1, 8x plus 5y equals 24. Let's multiply by negative 4. S2, negative 8x, negative 28y equals negative 24. Let's add. And so the x's cancel. I get negative 23y equals 0. Divide by negative 23. And so I get that y is 0. And so let's use S1 to determine x. 8x plus 5 times 0 equals 24. So 8x is equal to 24. Divide both sides of my equation by 8. And so I have here x is equal to 3. So let's figure out z. I can use any of these. Actually, that's just as easy. Why don't I use R3? It doesn't really matter. I'll use R3. X plus Y plus Z equals 5. And so subtract 3 from both sides. And so Z is equal to 2. Okay, good. Let me do problem number 29. An underdetermined system. And so R1, 2x minus y plus 6z equals negative 5. R2, x plus 5y minus z equals 7. So in this case, I guess I'll eliminate y. So let's multiply by 5. And so eliminate. So I have 5r1, 10x minus 5y plus 30z equals negative 25. And I have R2, x plus 5y minus z equals 7. Let's add. So I get 11x, the y's cancel, plus 29z equals 18. Well, that's all nice and fine, but you only have two equations, so you've used them all to eliminate one variable. And so this is what's called a underdetermined system. Because it has less equations than variables, so it's underdetermined. And so in general, these usually have a lot of solutions. So in this case, it actually has an infinite number of solutions. And so, I don't know, let's say that I let. So now let's write this in terms of some sort of variable. This will actually be a one parameter family solutions. And so let, I don't care, x equal 29, call it any variable I want. I'll say alpha, you could, or let's say t. Let's say t And so I have, so maybe I'll call this S1. So I have 11x plus 29z equals 18. In this case, I guess it doesn't matter because they'll get 11, 12. Okay. It's not going to simplify it that much. Eh. Okay, so actually, let me just call it t. So actually, I changed my mind. Let x equal t. So I get 11t plus 29z is 18. And so let's subtract 11t from both sides of my equation. So I get 29z equals 18 minus 11t. Divide both sides of your equation by 29. And so I get that z equals 18 minus 11t over 29. And x is equal to t, so I can use any equation. Doesn't really matter. None of them will be that nice. Let's use R2. And so x, which is just t, plus 5y minus z equals 7. Let's multiply both sides of my equation by 29. And so I get 29t plus, I guess let's multiply 29 times 5, 145y, minus, the 29's cancel, so the negative outside makes that 18 and negative, and the negative and negative 11 makes that positive 11t equals, let's multiply the 29 times 7, 203. Let's combine like terms. And so 29t plus 145t plus 11t is 185t minus 18 is equal to 203. Let's add 203 to both sides of my equation. I'm sorry, 18 to both sides of my equation. And so 185t is equal to 221. Divide both sides of my equation. By 185. Oops. And so I get that t. Wait, what? What? What in the world? Oh man, this is garbage. Okay, let's try that over again. Sorry about that. I guess I can only do one thing at one time. Um, let, let me do combine like terms. 29t plus 11t is 40t plus 145. Y minus 18 is 203. Let's add 18 to both sides of my equation. Subtract 40t from both sides of my equation. And so you get 145 y is equal to 221 minus 40t. Divide both sides of your equation by 145. And so you get y is equal to 221 minus 40t over 45. So therefore, and let's actually write the solution then. My solution has the form x is equal to t, y is equal to 221 minus 40t over 45, and z is 18 minus 11t over 29. And that is your solution. This is a line in the plane. And so the intersection of these two planes turn out to be a line in 3 space. Let me do problem number 32. R1, 2x minus y plus 2z plus w equals 1. R2, x plus y plus z plus minus w equals negative 1. R3, 3x plus 2y minus z plus 2w equals 6. R4, x minus 3y plus z minus 3w equals negative 3. Okay, so if I look at this, let me just check if all these are correct. 2, negative 1, 2, 1, 1, 1, 1, 1, negative 1, negative 1, 3, 2, negative 1, 2, 6, 1, negative 3, 1, negative 3, negative 3. Okay, good. Had to check that I actually wrote the problem down correctly. So here it looks like the z's are actually slightly easier to solve for than any of the other. So eliminate z. So let's eliminate z. And so let's add R2 plus R3. 3x plus 2y minus z plus 2w equals 6. So if I add these, I get 4x plus 3y plus W equals 5. So let's call that S1. Let's do R3 and R4. 3x plus 2y minus z plus 3x plus 2y minus z plus 2w equals 6. X minus 3y plus z minus 3w equals negative 3. Let's add these. Let me just check. Okay, I think I've written these down correctly. So let's add these together. And so I get 4x minus y minus w equals 3. So that's S2. So I've used R2, R3, R4. I have not used R1 yet. So let's do R1, 2x minus y plus 2z plus w equals 1. And let's do 2R3 and then add those. So 2R3, so 6x, 4y minus 2z, 4w, 12. Let's add these. So 8x plus 3y, z's cancel, plus 5w equals 13. So that's S3. Okay, so let's just collect these and write them all in one location. And so S1. So I've gone from 4 equations, 4 unknowns, to now having 3 equations with 3 unknowns. Well, that's good. That's just where we were on the previous problem. So we're getting ahead. So we're almost done then. Now we just have to solve a system of 3 equations in 3 unknowns. Okay, so I guess I will eliminate W, because that looks pretty easy. Yeah, the W's. So I'll eliminate W. Okay, so let me do that. So S1, 4x plus 3y plus W is 5. S2, 4x minus y minus W is 3. So let's add these. So I get 8x plus 2y equals 8. Let's divide everything by 2. And so I get x plus y equals 4. RS, let's call this t. Okay. So I've used the first 2 equations. I've got to use the third. So let's do 5s1, S2, 20 minus 5 minus 5, 15. And let's do S3, 8, 3, 5, 13. And let's add. So I get 28x minus 2y, the w's cancel, is 28. Divide by 2. And so now I get 14x minus y equals 14. So let's call that T2. Notice if I add T1 plus T2, the y's are going to cancel. And so I get 18x equals 18. Divide by 18. So x is equal to 1. Okay, good. So now I can use, let's say T1, 4x plus y is 4. So 4 plus y is 4. Subtract 4 from both sides of your equation. And so y is equal to 0. And lastly, so I have x, y. Let's figure out the w, I guess. So let's use S1 to figure out w. And so S1, 4x plus 3y, 4x plus 3y plus w equals 5. 4x plus 3w, there it is, good. 4x plus 3w equals 5. And so I have 4 plus w is 5. Subtract 4 from both sides of my equation. So w is 1. And so let's figure out z, I guess. So I have x, y, w, but I didn't figure out z yet. And so there's z. Let's do R2. Let's do R2. Okay, so let's figure out R2. X plus y plus z minus w equals negative 1. And so I have 1 plus z minus 1 is negative 1. The 1's cancel. So z equals negative 1. So x is 1, y is 0, z negative 1, w is 1. So I've solved the system. Good. Let me do problem number 40. 46. Let me do problem 46. So let me do problem 46. Oh no. Oh, good, good. So let me do problem 46. R1. 2x minus 3y minus z equals 0. R2 x plus 3y minus 2z equals 0. R3 x minus 3y, oops, minus 3y equals 0. So maybe eliminate z, because there's no z in R3. So let's eliminate z. Okay, so let's take negative 2 R1. That's a negative 4x plus 6y plus 2z is 0. Let's add to it R2. X plus 3y minus 2z is 0. Let's add these. So I get negative 3x plus 9y is 0. Actually, let me divide by, well, let's just call this, well, let's divide by negative 3. And so I get x minus 3y is 0. Notice this equation, I'll call it S1, is actually the same as R3. So if I do minus R3 and I add them, I get 0 equals 0. Okay, so it means I can eliminate that. So I just have S1. And so let y equal t, in which case I did 32. I see. I didn't do the home. By the way, I forgot to tell you, since the right-hand side of this equation is 0, these are called homogeneous equations. So in exercises 34 through 50, solve the homogeneous system of equations. When the right-hand side is not 0, they're called non-homogeneous. So I was solving non-homogeneous equations. And so I have y equals t. So that says that from S1, x minus 3y is 0. So add 3t to both sides of your equation. And so x is equal to 3t. Okay, good. Let's use, I don't care which one. Let's say R2. So R2, x plus 3y minus 2z equals 0. So 3t plus 3t, 6t minus 2z is 0. Subtract 6t from both sides. So negative 2z equals negative 6t. Divide by negative 2. So z equals 3t. And so the solution is x is 3t, y is t, z is 3t. So again, I have a one parameter family solutions. This is a, so I should actually say that. This is a one parameter family of solutions. This is a line in the plane. Let me do problem number 50. X plus 6y plus 3z plus 8w equals 0. R2, 2x plus 4y plus 6z minus w equals 0. 3x plus 10y plus 9z plus 7w equals 0. R4, 4x plus 16y plus 12z plus 15, w equals 0. Okay, so first thing to notice is they're trying to mess with us. Notice R1 plus R2 is R3. So let me just show you that. And R1 plus R3, where I can is equal to R4. Okay. Meaning that two R1 plus R2 is equal to R4. So if you just double, yeah, and I'll probably show you that. Yeah, maybe I'll just do that. So that then you can see that R3 and R4 can be eliminated. So 2R1 plus R2 is R4. And so let's show that. So thus, we can eliminate equations R3 and R4 because they are just written in terms, they're really just a rewriting of equations R1 and R2. So basically, it's a case where these are just sort of linear combinations of the others. So they're subspaces of the other space. Okay, so let's show this. R1 plus R2. Let's show you that that's R3. So R1 plus R2. Let's add these. 3x plus 10y plus 9z plus 7w is 0. And let's look. That is the same as R3. Now let's look at what I said, 2R1, 2x plus 12y plus 6z plus 16w equals 0. And let's look at R2. 2x plus 4y plus 6z minus w is 0. So let's add these. So if I do that, I get 4x plus 16y plus 12z plus 15w is 0. And let's look. 4x, 16y, 12z, 15w. That is just R4. So really, I only have R1 and R2. So let's just deal with R1. And R2. So really, those are the only two equations that I have. So really, I can actually only eliminate one variable. And so I guess what I'll do is I guess I'll eliminate W. So let me eliminate W. Okay, so let's take R1, X. Actually, it'll be easier not to eliminate W. Let's eliminate X. So I'll do -2. That'll give me at least smaller numbers. R1, -2x, -12y, -6z, minus 16w equals 0, plus R2, 2x, plus 4y, plus 6z, minus w equals 0. So let's add these. So the x's cancel. So I get a -8y, z's cancel, minus 17w equals 0. So let's say w equal 8t. Doesn't really matter. I could make it, yeah, I'll just leave it as positive. Okay. And so that says that -8y minus 17t, that's 8t equals 0. So one of them's going to have to be negative, and I guess it doesn't really matter. So let's multiply 17 times 8. So I get a -8y minus 136 t equals 0. Let's add 136t to both sides of my equation. So you get -8y equals 136t. Divide both sides of my equation by -8. And so t is going to equal -17. So y is going to equal a -17t. Okay, so let's figure out what x is. So let's use, I guess I'll go to R1. And so R1 says x. by the way, this is going to be a two-parameter family of solutions, not just one parameter. So the other one I guess I'll call S. So x plus 6y. Actually, let me use a little bit more space. And so R1 x plus 6y plus 3z plus 8w equals 0. And so I have here x minus 102 t plus 3z plus 64t equals 0. Make that look a little nice. And so I have x plus 3z minus 38t is 0. So I have, I guess, let z equal s. Then this equation becomes, let me do minus s, because then it'll be x plus 3z minus 38t equals 0. And so I have x minus 3s minus 38t is 0. Add 3s, 38t to both sides of your equation. And so I have here x equals 3s plus 38t. Therefore, my solution is 3s plus 38t. My s's look like 5s. 3s plus 38t. Y is negative 17t. Z is negative s. X, Y, Z, W is 8t. And so this is a two-parameter family of solutions, which means that this is actually a plane in, let's see, this is 4 space. So this is a two-dimensional plane in a 4-dimensional space. So this is a two-parameter family of solutions. And so the solution, so this is a two-dimensional I'll just leave it at that. Okay, let me do maybe one more of these. So that was, let's see, that was number what, 50? 50. Oh, these are getting longer. Okay, so let me do problem 54. A dietitian is preparing a meal consisting of 3 types of food. Food A, food B, food C, yummy, An ounce of food A contains 3 units of protein, 2 units of fat, 5 units of carbohydrates. Um, each ounce of food contains 2 units, 2 grams, I guess, of protein, 3 units of fat, 1 unit of carbohydrate. Each ounce of food C contains 2 units of protein, 4 units of fat, 3 units of carbohydrate. A patient must receive 38 units of protein, 50 units of fat, 50 units of carbohydrate. How many ounces of each type of food should you use? So let's call A the number of units of type A, B the number of units of type B, C the number of units of type C. And so 3 type A has 3 units of fat. I'm sorry, 3 units of protein, 2 units of fat. Uh, so let's leave a little space here. So it has 3 units of protein, 2 units of fat, and 5 units of carbohydrate. That's food A. Food B has 2 units of protein, 3 units of fat. Food B, 1 unit of carbohydrate. Food C has 2 units of protein, 4 units of fat, and 3 units of carbohydrate. You want 37 units of protein, so this is your protein equation, 50 units of fat, so that's your fat equation, and 50 units of carbohydrate, so that's your carbohydrate equation. Let's call this R1, R2, R3. And so let me just check by the way. It's 325, 325, 231, 231, 243, 243, 37, 50, 50, 37, 50, 50. Okay. So I guess the easiest is to solve for B. So let's eliminate B first. Okay. And so let's take R1, 3A, 2B, 2C, minus 2R3, minus 10A, minus 2B, minus 6C, minus 100. Let's add these. So you get negative 7A minus 4C equals, let's see, 100 minus 37, 63. Actually, let me change all the signs. So you get 7A plus 4C is 64. So let's call that S1. Okay. Now let's do, I'm eliminating B. So let's do R2, 2A, plus 3B, plus 4C equals 50. And then let's do minus 3B, minus 3R3, minus 15A, minus 3B, minus 9C, minus 150. Let's add these. And so I get minus 13a minus 5c equals negative 100. And I guess let me divide by negative 1. And so I have here S2, 13a plus 5c is 100. Okay, well, there's nothing good there. So S1. So I guess what I'll do is I will multiply. Oh, I guess I'll eliminate C is probably the best one. So I'll do 5S1. So 35A, 20C, 320, and then negative 4C, negative 4S1. And so let's multiply 4 times, I guess, 13. So 52A minus 20C equals negative 400. Okay. So let me combine these. So I have negative 17A, the C's cancel, equals negative 80. Oh, that's not going to come out evenly. So that's just going to be A is 80 over 17. And so let's figure out what, let's use, doesn't really matter in this case since none of them are very nice numbers, but maybe I'll do S1. So 7A plus 4C equals 64. Multiply both sides of my equation, I guess, by 17. That'll at least get rid of my fraction. So 7 times 80, 560. Oh no, 560. The 17s cancel. 17 times 4, I guess. Plus 68. C is equal to 64 times 17. 1088. Subtract 560 from both sides of your equation. So you get 68C is equal to 528. So divide both sides of your equation by 68. And so you get C is equal to, let's see, I can divide 528 by 4. So that gives you 132. I can divide 68 by 4. 17. Okay. And then B. Okay, let's see. B, how about R3? So let's do R3. And so 5A plus B, 5A plus B plus 3C is equal to 50. Let me multiply both sides of my equation by 17. And so the 17's cancel. 5 times 80, 400, plus 17B, plus 3 times 132, 396. 17's cancel. Equals 17 times 50. 850. And so I have 17B plus 796 equals 850. Subtract 796 from both sides. And so 17B is equal to 54. Divide both sides of my equation by 17. B equals 54 over 17. And so I have 80 over 17 units of food A. 54 over 17 units of food B. And 132 over 17 units of food B, of food C. And that is your answer. So that really finishes off section 12.1. And I guess we'll start section 12.2 on Monday.